After successfully completing this lesson, you'll be familiar with series pumping, multi-stage, parallel pumping. Series pumping can be considered as a series of centrifugal pumps arranged to supply one another in series and thus progressively increase the discharge pressure. The illustration shows a cross-section through a typical vertical multi-stage single-entry centrifugal pump used for deep well cargo pumping. The pump drive is located outside the tank and can be electric or hydraulic. Here, a diffuser is fit to assist in raising the discharge pressure. It is a ring fixed to the casing around the impeller in which there are passages formed by vanes. The passages widen out in the direction of the liquid flow and act to convert the kinetic energy of the liquid into pressure energy in the same manner as a volute casing. Hydraulic balance arrangements are also customary. Some of the high-pressure discharge liquid is directed against a drum or piston arrangement to balance the discharge liquid pressure on the impeller and thus maintain it in an equilibrium position. In series operation, the discharge of one pump feeds the suction of a second pump. When two or more pumps are operated in series, the flow through all of the pumps is equal, since whatever flows through one pump has to flow through the next pump in series, provided there are no side streams. Let's take a closer look at pump curves. For the purposes of this lesson, you must create a pump curve chart for identical pumps used in series. Let's start by adding a head-to-flow curve for one pump to the chart. Let's add a combined head-to-flow curve for two identical pumps. Let's add a combined head-to-flow curve for three identical pumps. If pumps are used in series in a system, a combined pump curve can be generated analogous to the combined curve, though the combined curve is generated differently, of course. Again, the same general rule applies, namely that the intersection of the combined pump curve with the system head curve determines the total flow delivered to the system, and allows one to determine where on its own head-to-flow curve each of the pumps is running. For the purposes of this lesson, you must create a pump curve chart for identical pumps used in a system with a steep system head curve. Let's start by adding a head-to-flow curve for one pump to the chart. Let's add a head-to-flow curve for two identical pumps in parallel. Let's add the head-to-flow curve for three identical pumps in parallel. Let's add the head-to-flow curve for two pumps in series. This illustration shows that when the system head curve is very steep, operating a second pump in parallel with the first produces only a marginal increase in flow. If these same pumps were piped in series rather than in parallel, they would produce a higher flow through the system. The illustration shows that only two such pumps piped in series deliver more flow through the system than three pumps operating in parallel do. So the general rule is that if the system head curve is relatively steep, series pumping is probably more effective than parallel pumping for increasing the flow range of the pumps. The opposite is also true where fairly flat system head curves are concerned. Parallel pumping is probably more effective producing wide flow range than series pumping is. And finally, you must create a pump curve chart for non-identical pumps used in series. Let's start by adding a head-to-flow curve for one pump to the chart. The illustration shows the combined pump curve for two non-identical pumps operating in series. The combined curve is generated using the same procedure as for identically sized pumps. At the arbitrarily selected flow rates, the total delivered head of the two pumps are added together to produce the combined curve data point. It is common in pipelines to have several differently sized pumps, allowing the operators the widest possible range of flow and/or variation of products pumped. The specific speed of a centrifugal pump is the revolutions per minute at which a geometrically similar pump would run in order to deliver 1 cubic meter per hour against 1 meter head. It's derived by the following formula. The primary purpose of operating pumps in parallel is to allow a wider range of flow than would be possible with a single fixed-speed pump for systems with widely varying flow demand. Examples of applications for parallel pumping include municipal water supply and wastewater pumps, pumps and water-chilled heating, ventilating and air conditioning systems, main process pumps in a variable capacity process plant, and condensate pumps in a steam power plant. Usually there are no more than 3 or 4 pumps operating in parallel. When parallel pumps are being considered for a system design, the pumps must be carefully matched to each other and to the system to ensure that the pumps are always operating at a healthy point on their head-to-flow curves, and to ensure that the system is such that true benefits are achieved from the parallel pumping arrangement. However, this does not always turn out to be the case. In order to analyze a parallel pumping arrangement, it is necessary to construct the system head curve. Then, a combined pump curve must be developed, depicting the head-flow relationship for the pumps while pumping in parallel. Once these two curves are constructed, the rule for total system flow is that the total flow through the system is represented by the intersection of the system head curve with the combined pump curve. The illustrations show the combined pump curve is developed, with a system having either 2 or 3 identical pumps operating in parallel. If the system head curve is too steep, a situation which could be caused by an undersized piping system or by some other undersized component in the system which acts as a bottleneck, then it turns out that very little benefit is achieved by operating pumps in parallel in that system. The situation with two non-identical pumps operating in parallel is shown in the diagram. The curves of the two different pumps are combined in curve C by adding the flow of the two pumps at arbitrarily selected values of head. The combined curve is not a smooth one, due to the way it is generated as the graphical sum of curves A and B. The combined curve C actually follows curve A for a while, since the maximum head for curve B is lower than the maximum head for curve A. The same rule applies as before. The illustration shows that operating two non-identical pumps in parallel can present problems when the two non-identical pumps are mismatched for the system in which they're working. The system curve, labeled curve Y, is steeper than the one shown before. An attempt to run these two pumps in parallel in the system represented by system head curve Y would mean that the pump represented by curve A would operate at the intersection point of the combined curve and the system head curve, labeled point A, which is the same point it would operate at when pumping alone in the system. Congratulations! You've completed this lesson.